Hello, my name is Henry Chen, and today I'll be talking. Hello, my name is Henry Chen, and today I'll be talking about the first lab in Physics 2211, which is about Newton's second law and object moving in constant velocity. So in this lab, we'll be applying Newton's second law, also known as the momentum principle, in real life, and as we test it by rolling a ball-shaped object and then confirming our results with a Python simulation. In an ideal world where there is no friction, air resistance, or any other outside forces, we say that the net force acting on the ball is zero. And according to the momentum principle, the ball will continue to stay in motion for pretty much an infinite amount of time. However, we know that's not the case, since in real life there is air resistance and friction, which causes the ball to eventually stop. And I'll be using a golf ball in this experiment since it is relatively dense and its smooth surface will minimize the effect of the friction when it rolls on the table. So these are the two main formulas that we will use and in our Python model. So the first formula is updating the velocity, and it's based on Newton's second law or momentum principle. Pretty much says that the final velocity equals to the initial velocity plus F net divided by its mass times delta t. However, F net is zero, so this formula really just simplifies into final velocity equals to initial velocity, which means that the ball will be rolling at a constant velocity throughout the entire time duration. And our system will simply consist of the Earth, the table, and the golf ball. These are my initial conditions. The x-axis orientation, the ball will start at the origin 0, 0 and move right along the positive x-axis, which means that its x position will continue to increase. And this is the mass of the golf ball, and an initial velocity is 0.27 meters per second, which is calculated by averaging the velocity of the first 0.1 second that the ball travels using tracker. And this is delta t, which is 0.01 seconds. And it is the step that we will update the position and its velocity. So here, this is my tracker. As you can see, the golf ball will start initially from the center or at the origin and continue to roll in a positive x direction. Here we see the data collected, and this is the graph that we've generated from both the Python simulation here. And these are the stats that we get. And then we will compare it. We will compare it to the tracker data. And as you can see, they pretty much agree, as the position are pretty much the same. However, the simulation gave us a completely linear straight line, which also makes sense because our model is modeling a perfect world with no friction and air resistance. However, that's not the case in real life, so there will be some difference and some uncertainty. However, overall, I would say they symbolize, they pretty much agree in the results of the position of the golf ball. So this is a design choice that I made. I've decided to have the ball move in a positive x direction, which means that our graph will look like this. The slope will be positive. If I decided to have the ball move left or in a negative x direction, we'll end up a position graph more like this, which slopes negatively. So is it possible to say how many pushes and pulls have happened throughout the entire duration? I would say it's not possible, since there are too many complex factors that goes into simulating real life situations. In our case, in such a simple experiment, there is air resistance, friction from the golf ball itself, and friction from the table, which are both impossible to calculate accurately without its specified tools. We also cannot accurately calculate how much force we are pushing into the ball initially, as we're simply using an estimation. Considering the uncertainty and outside factors of our experiment, I'd say the results in analyzing movement came out relatively similar, as they both predicted a linear path and similar in slope. However, the uncertainty we predicted that there will be uncertainty, but the uncertainty aren't that significant. And I'd say that this model in Python does predict real life simulation pretty well.